Okay, all right. So we're going to finish off chapter 18 today. We spent a lot of last lecture talking about the first of these four functional groups, ethers, and now we're going to focus our attention onto these epoxides, and then we'll talk a little bit about thiols and sulfides here at the end as well. Okay. So epoxides, remember, are technically ethers because we got carbons on either side of this oxygen, but they're in this three-membered ring, right? So they're very kind of special in that these three-membered rings are not terribly unstable. They really want to open up, and so these tend to be very much so more reactive than normal ethers. All right. Before we get into the reactions of these epoxides, let's talk about how we make epoxides. Right, so preparation of epoxides. All right, and epoxides are something that we've already talked a little bit about because we introduced one method of making them starting from an alkene. All right, so let's just take a simple old alkene here. The first method was actually kind of a multi-step method. The first step, we react with bromine and water. And this produces what's called a halohydrin. You have the bromine attached to one carbon and the OH attached to the other carbon. Okay, and again, this is what we called a halohydrin. All right, and then if we treat this here in a second step with a solution of base, okay, dilute base, got some water present here, we will get this epoxide that forms. All right, and at the very beginning of the semester, these sort of Br2 alkene reactions are one thing that we reviewed. We're going to do our reaction mechanism here. These also go through a triangle-shaped intermediate here. All right, these reactions do not form carbocations. Instead, you get this cyclic bromonium ion intermediate. And just like an epoxide, this thing really wants to open up this ring here. If you just had bromine present, the other bromide ion would play the role of a nucleophile. But if you have water present, you'll have water playing the role of the nucleophile. And this ring opening step right here in this mechanism, this is the first time that we were introduced to this with these bromonium ions. We're going to see this over and over again with our epoxides as well. All right, so now we're almost there. We just have to deprotonate that. Let's just do it. And since we have a bunch of water floating around, water can be our proton acceptor. I guess I gotta keep my bromine over here. All right, so this step here, let's just note, We got this pair of electrons on my oxygen. That's going to form my new bond with this carbon. This carbon right here is playing the role of what? The nucleophile or the electrophile in this reaction? The one getting attacked, right? So it's the electrophile. Remember, the arrow always points towards the electrophile. All right, and then this pair of electrons that was in that bromine-carbon triangle bond here is what jumps up and becomes a lone pair. The bromine also had this bond over here, and that remains in our product, right? So that's this ring opening reaction. This triangle's opening up. Our bromine is losing one bond, gaining that pair of electrons, but it still maintains the bond on the other side. All right, so I feel like it's going to get too busy if I move on with all these colors here. So okay, so then the next step in this mechanism here is pretty cool. It's fairly simple in that we just have a base and we have an acid-base reaction. Okay, so I'm going to save some space here. I'm going to erase my sodium and replace it with a minus sign because that sodium's not doing anything in sodium hydroxide. Right, so that base is going to grab that proton, kick up that pair of electrons. Okay, this forms one of those deprotonated alcohols. Does anybody remember what we call a deprotonated alcohol? A something oxide. An alk oxide, because it's got that alkyl part to it. In this case, there's this bromine as well. But yes, we have this deprotonated alcohol. And then this thing reacts with itself. Right? So this oxygen, you know, we have a good nucleophile and a good leaving group all in the same molecule. So this oxygen is going to attack a carbon in the same molecule and kick off that good leaving group, the bromide ion. And so that's how we have this ring that's formed here. Okay. Cool. So anyways, if we're just going to kind of simplify everything here, this is a mechanism that we went over. Good thing to review here because it's something that we should know. But just our list of reagents here would be first step, bromine and water. Second step, sodium hydroxide. That's one way we can create an epoxide. Actually, yeah, I lied. I said water up here. That was wrong. All right, so this is one way to do it. There's another fancier way to do it that is kind of a go-to method of preparing epoxides. I guess it just works super well. And that is using what's called a peroxy acid. And these have this formula. A peroxy acid has the formula R bound to a carbonyl carbon. All right, so this is this peroxy acid group here. What does it look a lot like in terms of functional groups that we've studied before? Yeah, it looks a lot like a carboxylic acid with this extra oxygen in the middle here. You have this weird oxygen-oxygen single bond. Those are very rare, okay? It turns out that because of this, this thing is very reactive. Again, it will take an alkene, an alkene plus our peroxy acid. And by some magic, it is able to insert that oxygen between that existing carbon-carbon bond, right? So it takes that carbon-carbon pi bond and it sticks an oxygen in the middle of it. That same oxygen, that was that kind of extra oxygen in our formula here. And then the other product is then just a carboxylic acid. This isn't something that we're going to learn the mechanism for, so for our purposes, it magically sticks that oxygen between those carbons in that carbon-carbon pi bond. These are very reactive. Because of that, there is one that's used as kind of like the go-to peroxy acid. It's nice and stable, it stores well, all that sort of stuff. And this is meta-chloro peroxy benzoic acid. All right, a benzene ring, and meta to one another, we have a chloro group and that peroxy acid group. All right, and it's all well and good to look at the structure and everything like that, but more importantly, you need to be able to, in terms of like list of reagents, be able to spy the, what the heck are they called? MCPBA. Meta-chloro-peroxy benzoic acid, but MCPBA is how it's written in like a reagent list. An acronym, holy crap, that was going to drive me nuts. The acronym is what you need to be able to recognize. So for example, we wouldn't like draw out the structure explicitly, you could, but for example, if I gave you an alkene, and I said treat this thing with MCPBA. All right, everybody take a second and draw me the product here. All right, so in place of that carbon-carbon pi bond, I'm going to stick my epoxide functional group, right? That triangle with the oxygen at the top. Cool. All right, so now we've figured out how to make them. Let's talk about reactions of epoxides. All right, and the one thing that you want to have in your mind when we're talking about reactions of epoxides is this term ring opening reactions. All right, if we look at the structure of an epoxide, There is a ton of angle strain in this triangle. Remember, bonds on an sp3 hybridized carbon want to be at like 109 degrees. In a triangle here, that's 60 degrees. So they're forced into this uncomfortably tight angle, which makes these bonds fairly weak, right? Ready to break, ready to just pop this triangle open, okay? And so in terms of our organic chemistry terms here, that makes this carbon right here a really good electrophile because this oxygen is going to play the role of a leaving group. All right, so what we're going to see over and over again for these epoxide reactions, there might be a little bit of a twist on it here or there, but there's going to be some nucleophile that does what nucleophiles do and attacks that electrophilic carbon, causing that ring opening to occur. All right. So these epoxides are a good time to sort of review what we had discussed about the conditions in which we do reaction mechanisms. These are going to be fairly simple reaction mechanisms, but epoxides react both under acidic conditions and under basic conditions. And we can tell when we draw a mechanism whether it is an acidic condition mechanism or a basic condition mechanism. You can see by the charges on your intermediates, okay? So let's review that real quick because we have not done that this semester yet. We're going to start with what I think is the easier of the two, and these are basic conditions mechanisms. All right, so the real rule if you have a mechanism under basic conditions is that you can have no strong acids. Okay, any sort of acid intermediate, it won't exist, it won't survive because you're in basic conditions, right? That donatable proton is just going to be ripped off immediately. Now, if we look at the structure of our good acids, things that are considered to be good acids in organic chemistry, a lot of them have this same sort of feature in terms of their charges, which they're protonated, so they have this positive charge, right? So we can kind of simplify this rule of no strong acids to make it something that's even easier to see in our mechanisms, which is we should have no positive charges. All right, all of our intermediates are either neutral or negatively charged. All right, so we said that epoxides are going to be playing the role of electrophiles in this reaction, right? So that means that our other component in our reaction is going to be the nucleophile, and most good nucleophiles are basic. Or rather, will work under basic conditions. Like, I mean, if we just want to think of a few structures here, right? A good nucleophile would be something like an alkoxide ion. or a carbon with a negative charge, like a cyanide ion, or even a Grignard, another nucleophile that you could not use under acidic conditions, right? So these are all basic condition nucleophiles here. And we can tell that they work under basic conditions because they have these negative charges, right? None of these are positively charged. A good nucleophile is electron rich, so it's negatively charged. So these would all work as basic nucleophiles here. Okay, so if we take an so now let's look at, I guess we can look at this simple example here. We just use generic nucleophile. All right, and we're going to see these ring opening reactions here. So everybody take a second and draw me my next step in this reaction here, given these electron pushing arrows. So now my ring has opened. I have my nucleophile on one carbon and that alkoxide ion on my other carbon. Okay, and this is something that we're going to see over and over again in these epoxide reactions, in these ring opening reactions. Like if I color these carbons, one of them blue and one of them red, notice that the one that got attacked, the red one, that now has my nucleophile, and the next door neighbor, the blue one, that's what has my oxygen, right? And so a signature of these epoxide reactions, these ring opening reactions, are going to be, thank you, are going to be that they are located 2 carbons from one another, right? These two functional groups, the oxygen from your epoxide and whatever your nucleophile, are located 2 carbons apart. Okay, now we don't stop there. There's going to be one more step, which is to protonate that alkoxide ion. Okay, so there's always a second step where you either follow it up with some source of proton. Waters would actually just work. Typically they would put in like a weak acid because that would stop the reaction. It would help neutralize any nucleophile left over. All right, but if we want to be good and just do our mechanism here, that alkoxide ion's going to grab a hydrogen. Okay, and again, a signature of these reactions, just to hammer this home here, is that your 2 new functional groups, your hydroxyl and whatever your nucleophile was, are 2 carbons apart. All right, so let's just look at another one. We're going to use a little bit more complicated of an epoxide. Okay. And let's look at an actual nucleophile here. We'll take our cyanide ion. All right, and again, I'm going to color these carbons on my epoxide so we can keep track of which is which here. Okay, now for this particular nucleophile here, or rather for this particular epoxide, it's no longer symmetric, right? So I'm going to get a different product if my nucleophile attacks the blue carbon than I am if my nucleophile attacks the red carbon. So let's see if we can think through which one it would be here. First of all, if we notice in this first step here, we have the nucleophile attacking and the leaving group leaving all in one step. And what do we call these substitution reactions, where the nucleophile attacks and the leaving group leaves all in one step? SN2. Okay, so this first step here in this reaction is going to be an SN2 substitution. All right, so then which one of these is going to be more likely? My nucleophile attacking that blue carbon or my nucleophile attacking that red carbon? I want everybody to think about it for a second, and then we're going to take a poll here. All right, so let's see. Who thinks that the nucleophile is going to attack the blue carbon? And who thinks the red carbon? So why the blue one? Yeah, we would call it, in the chemistry way, we would say it's more accessible, right? It's not as crowded. It's nice and open, right? So absolutely, these SN2, we've seen this before. These nucleophiles are going to prefer the more accessible carbon. So nucleophile attacks the more accessible carbon. So in this case, yes, it's going to be this blue one here. All right, I want you guys to finish this mechanism. I put in that first electron pushing arrow. All right, I want you to finish this mechanism here. I will say that there's going to have to be a second step with that H3O+. But yeah, let's see if we can't get our products here. I wanted to pick this cyanide, this nitrile group here, to make sure that we're going to draw it correctly. Right? That carbon-carbon triple bond means we have to draw that all in a straight line there. And it's one of those things that your homework system would let you get away with doing it sloppy, but I'm going to take points off on the exam if you do it sloppy, right? Our triple bonds have to be linear. Okay, and then, sorry, I'm missing also my oxygen with its negative charge. Okay, so in terms of what we would call the regioselectivity of this reaction, where do you put your nucleophile? Because it's an SN2 reaction, the nucleophile is going to attack the more accessible carbon. Okay, you'll always get like a mixture of products, but this one's quite heavily favored here, comparing a primary carbon to a tertiary carbon. Okay, so now we're going to look at the same type of reaction, right? Just another ring opening reaction of these epoxides where nucleophile attacks that electrophilic epoxide, but this is now going to be under acidic conditions. Okay. Acidic conditions mechanisms. Acidic condition mechanisms. Okay. So similar to before, like under basic conditions, the simple rule when you say that you have a mechanism under acidic conditions is you can't have any strong bases. A hydroxide ion is not going to survive under acidic conditions, right? That can't possibly be one of your reagents in your reaction. And similar to before, our strong bases all have this common feature with their charges, and that they are negatively charged. Right? So then all intermediates should be either positively charged or neutral. All right, now there is a notable exception to this rule that we want to put down, because these are ions that have a negative charge, but they are just trash bases, and those are our halogens, right? So we can say there's an exception to this rule. A chloride ion, a bromide ion, an iodide ion, all of these will survive just fine under acidic conditions, because even though they have a negative charge, they are not strong bases. They are in fact terrible, terrible bases. And it turns out that they're great nucleophiles, so it's a very important exception to make note of, right? These are going to be ones that are primarily used under acidic conditions. Okay, other acidic condition nucleophiles. Okay, the other ones that you're going to see playing the role of a nucleophile under acidic conditions, we can just, I guess, say our chloride ion, our bromide ion, and our iodide ion. These are all great nucleophiles. Okay. The other ones would be considered more weak nucleophiles because they're neutral nucleophiles. So for example, water would be an acidic condition nucleophile. That thing can exist under acidic conditions, and it can play the role of a nucleophile. Same thing as an alcohol. All right, so these are going to be most of your neutral nucleophiles which can exist under acidic conditions. An important, I guess just because we're on this trend here, ammonium cannot be an acidic condition nucleophile. It's too good of a base, right? So oxygen's really going to be the one, aside from your halogens, oxygen's the atom you're going to see playing the role of a nucleophile under acidic conditions, okay? Another one would be, instead of oxygen, that neutral, we replace it with an S, or our thiols. These would also work under neutral conditions, or under acidic conditions. Okay, cool. So then let's take one of these acidic condition nucleophiles and let's react it with our epoxide. We're going to use our simple epoxide here. going to take a bromide ion. All right, and we're going to try to figure out this mechanism here. Okay, so first, let's just do what we did before. Let's have our nucleophile attack our electrophile and have our ring opening reaction occur. All right, that would make it so we have a bromide on our bromine, a bromo group on one, and my alkoxide on the other. Okay, so, right, the whole point is, let's say that we don't really know what we're doing other than that we have a reaction under acidic conditions. How do I know that I made a mistake here? I have that negative charge. I have this strong base right here. These alkoxide ions are great bases. This isn't going to survive under acidic conditions. All right, and so what we're going to see, and this is going to hold true for the more advanced mechanisms that we learn here in future chapters. These are relatively simple here, but this is going to be a strategy that we use over and over and over again to manage our charges. Okay, we're going to manage our charges using proton transfer steps. Okay, this is a strategy we're going to use over and over again, especially in this next chapter when we start getting really mechanism heavy. When we say we have a reaction that takes place under acidic conditions, we can't have something like this, right? So how can I avoid getting an intermediate like this that has a negative charge? Okay, how about instead in our first step, we protonate that oxygen. We do a proton transfer to that oxygen. All right, so if we're under acidic conditions, I can throw in a hydronium ion. If it specified a particular acid, I could use that formula as well. All right, but our first step here instead, let's protonate that epoxide oxygen. Now I can do my ring opening step, my SN2 reaction here. The bromide will come and attack, and that will lead to this ring opening reaction. And notice that by protonating that oxygen first, now when that ring opening reaction occurs, I don't have this alkoxide ion, I already have a protonated oxygen. So I just have a hydroxyl group. Right? So this first one we said was wrong. We can't do that because we're under acidic conditions. So instead, we used a proton transfer step. And that allowed us to avoid a negatively charged intermediate. Okay, so in the context of these epoxides, it's just this two-step mechanism here. But again, this principle is going to hold true for some of the more complex mechanisms that we see in the future, where if you ever run into a situation where you're making your way towards the product, but you're like, oh crap, I can't have a negative charge in there. Well, take a step back and do a proton transfer step, and that will help you avoid that charge that you're not allowed to have. Okay, so that's for our epoxide reactions here. The one thing that we got to cover left here with these, okay, is there is something weird. Let's just take a look at an example before I give it away. All right. Okay, so we have our epoxide. Now we have an asymmetric epoxide here. And we're going to title this this section the regioselectivity of these ring opening. All right. So I'm going to use just generic nucleophile under basic conditions. And this is like the example that we did previously using that cyanide ion. And what did we say about that nucleophile attacking? Which carbon is it going to attack? The red or the blue? The blue one, right? Because it's the more accessible carbon. So we'll get our ring opening reaction. Keeping my colors consistent here. Okay, so under basic conditions, again, SN2, always the more accessible carbon. If we do the same reaction, but under acidic conditions, again, we'll use just generic nucleophile, bromide ion, chloride ion, something like that. All right? It turns out that under acidic conditions, unexpectedly, your major product will have your nucleophile having attacked that tertiary carbon as opposed to the primary carbon. Oh, whoops, I put a BR. I meant generic nucleophile, NU. All right, and this is pretty unexpected because this would also be considered an SN2 step. Your nucleophile attacks at the same point in which your leaving group leaves. All right, but the difference here, the explanation is that when we do a reaction under acidic conditions, we go through this protonated intermediate here. Right? That oxygen really wants a pair of electrons, right? It's currently got this positive charge. So because of that, this structure right here ends up sort of kinking itself to have this partial positive charge. Whoops. We got this half broken, half formed bond here with this partial positive charge on this carbon. Because it's a tertiary carbon, it's sort of happy bearing that positive charge. So the bottom line is that this bond right here is especially weak because of that tertiary carbon. Right? It doesn't stay in that perfect little triangle. It already starts to make some distance away from that carbon because that carbon is a tertiary carbon and can have some and can stably bear positive charge. It doesn't full-on break and form a full-on carbon carbocation intermediate. It's in this weird like halvesies state. All right, so under acidic conditions, and this is only true for a tertiary. So under acidic conditions, what we're going to say is that a tertiary carbon is going to win. All right, that's going to be the first thing that gets substituted. If it isn't a tertiary carbon, though, then just the sterics rule, the accessibility rule follows. So it would be a primary, and then lastly, would you have a secondary carbon substituted? All right, so this little half-formed, half-broken here would be our transition state for these acidic condition reactions. Okay? All right, so we're going to switch gears here and start talking about these last two functional groups, thiols and sulfides. Okay? One thing that we can sort of note here, when we made our list of good basic conditions nucleophiles, anything with a negative charge, one of the things that I guess we could have included here is if you have a deprotonated thiol, a sulfur with a negative charge. When we made our list of acidic nucleophiles, right, we also saw sulfur on that list. Sulfur is just a great nucleophile, and it's even better of a nucleophile because it's such a shitty base. So it only really prefers substitution type reactions. Okay? All right, so talking now about thiols and sulfides. One of the principles that we're going to see throughout these reactions here, so let's just make a note here, is that sulfur is a good nucleophile and a bad base. So it very much so prefers substitution reactions. All right, so let's say that we take this alkyl halide and we react it with this here. I want everybody to take a second and tell me what the product of this reaction would be. All right, so what do we know about our alkyl halides? Well, bromine's a good leaving group. Which makes that carbon a good electrophile. And as we established, sulfur is a good nucleophile, so nucleophiles are going to do what nucleophiles do. Attack our electrophile and kick off that leaving group. Right? So from this substitution reaction here, we would have created a thiol. Okay? So, on pencil and paper, it's like, okay, great, that's a great way to prepare thiols. But there's a problem here, right? On pencil and paper, I have one alkyl bromide drawn, and one of these nucleophiles and one of my thiols. But of course, when you carry this out in the lab, you don't have one molecule, you have a whole freaking beaker full of a bajillion of them, right? So at some point, I'm going to have formed my thiol, and I'm still going to have a bunch of my alkyl bromide floating around. So what's going to happen? Because as we established, this alkyl bromide is a great electrophile. It's got a good leaving group on there. And as we've established, sulfur is just a banging nucleophile. So what's going to happen between my thiol and my alkyl halide? I'm just going to have yet another reaction that occurs between that nucleophilic sulfur and that electrophilic carbon in my alkyl halide. Right? So this isn't really a preferred method of creating thiols, because instead you create sulfides, right? Or at the very least, a mixture between the two that you're going to have to figure out how to separate them out. Okay, if we're being good at this step in our mechanism, we have this protonated sulfide. So I'm going to need some base to come along. I'm just going to use generic B for base. All right, so we do know that sulfur is a great nucleophile, but it's almost like too good of a nucleophile because it'll just keep on reacting and reacting. So this method here would be a great way of producing a sulfide, not a thiol. Or again, you probably get a mixture of the two, and then you got to sit there and separate them out. Okay. So there is a fancy method of preparing a thiol that we're going to learn about. Okay, and this uses a compound called thiourea. Alright, so if you take your alkyl halide and you mix it with thiourea, again, the sulfur is going to play the role of a nucleophile, attack that electrophilic carbon, and kick off that leaving group. Alright, but everybody take a second and draw me my product here. Alright, so the sulfur is effectively bound to that electrophilic carbon, but it's still got all that other crap on the back end. And it's not just a hydrogen that you can add a base and, not something that can be just removed very easily. Alright, so it's kind of stuck like this. And then in a second step, you come along and you add in a dilute base. And that will leave you with a thiol. All right, your other product here, which is the one that we don't really care about, but it's kind of a famous molecule in organic chemistry. This molecule here is urea. All right, so just like a fun fact history lesson here, urea is a very famous molecule in organic chemistry. It kind of helped kick off the branch of organic chemistry. Even after chemistry had been like accepted as a science, when people were like, okay, fine, the world around us is made up of atoms, great. They still for a very long time felt that human beings were made up of something special, right? God made us, and we gotta be different than the rest of the world out there. We're not the same stuff as the rocks and the trees. We're our own special stuff, right? And that was kind of a guiding principle throughout science for a very long time. It was something that was very hard to shake. And this urea right here really helped with that because somebody had synthesized urea from scratch in the lab, and then they were able to isolate that compound from the human body, from urine, and prove, boom, boom, look, we got the same thing in both cases. All right, great. So it helped put one of those big cracks in this influence that like religion had about us being special and not being made of the same stuff as the world around us, and kind of helped birth organic chemistry as its own branch of chemistry. So yay, urea. Good for you. Okay. Anyways, this would be a way to convert an alkyl halide into a thiol without any of that sulfide byproduct. What's up?
Urettes?
Oh, in the back hall. Yeah, a whole rack of them. Yeah, for sure. We don't need them today. Feel free to take as many as you need. Okay, cool. So we are going to do a little bit of nomenclature, but we're going to save that for next class here because I just want to practice these reactions that we covered today. All right, so for the rest of the class here, we're just going to try to go through and practice all of these various reactions that we learned. Okay, make a little reaction wheel here, and you guys tell me what the product of these reactions are. so let's go through these. So first of all, that MCPBA, what does that do for us? An epoxide, right? So that's one of our methods for preparing an epoxide. So I'm going to replace that double bond and add an oxygen right in the middle. Okay, so I'm going to take that epoxide and I'm going to treat it with these two compounds here, HI. I'm going to color this carbon right here in blue and this carbon right here in red. All right, HI, which one am I going to add my iodide to? Red or blue? Blue. How do we know it should be blue? Yeah, because HI is one of our strong acids, right? Actually, probably the strongest acid that you can buy on the market. All right, and so yes, absolutely, this is going to be an acidic condition mechanism, which means that we're going to be adding to the more substituted carbon, surprisingly. Just make room. So absolutely, I'm going to put it on the blue carbon. That means that my red carbon gets that OH group. Okay. Now what about this NaO with an ethyl group on the end of it? That would be basic, right? So remember, what do we do whenever we see a compound like this? What should we do? Take out the sodium. This sodium isn't doing anything, and replace it with a minus sign. That'll show you who's really participating in the reaction here. And absolutely, this is an alkoxide ion, so a basic nucleophile. So that's going to attack the less substituted carbon. Okay, so now I'll have my OH group on the blue carbon. And I will instead have this ether group, I guess. This ethoxy group on my red carbon. Okay, I guess to be fair, I would have had to have had some step or either water or a weak acid in order to protonate that oxygen. I'm going to assume that that second step was there. All right, so then we're going to go here down to these, starting with an alkyl halide now. All right, we got two different products. Okay, with this thiourea, what's my functional group in my product? The thiol. So that's the way to just get that one substitution reaction that will leave you with the thiol. And if instead I used SH2, what would be my product? My major product, I guess, yeah. So this would be a great way of preparing instead a sulfide. Okay, so then lastly, what if I took my, or I guess let's just note here, we can also combine an epoxide with a thiol, right? Because that's also a good nucleophile. Okay, so if we did that under acidic conditions, everybody take a second and tell me what my product would be. Again, since we're under acidic conditions, it's going to attack the more substituted carbon, or at least the tertiary carbon. I don't want to say the more substituted. Okay, so then the last two, let's just think here. Now let's start out with a cyclic alkene. Okay, what if we did our Br2 and H2O followed by NaOH? All right, so what am I going to create with bromine, water, followed by sodium hydroxide? Again, an epoxide. This was our second method for creating an epoxide. And if I treat it with sodium hydroxide, what's my new functional group that I'm going to have in my final product here? I'm going to have an alcohol group for my epoxide oxygen. And what else am I going to have on my other carbon? So again, let's look here. We're going to do what with this sodium? Get rid of it. So my nucleophile here is going to be this hydroxide ion. If this thing attacks, and I get this ring opening reaction that occurs, I have just a diol. Right? My oxygens are on neighboring carbons here. All right, but this would actually not be full credit here because we are ignoring our stereochemistry. So let's think about our stereochemistry of our epoxide here. When this epoxide forms on my ring, I can't use these just straight up straight line bonds because there's not this ambiguous stereochemistry, right? Instead, I will have to put them both on either wedges or both on dashes, right? We can't have it can't be that one bond is pointing up from the ring and the other bond is pointed down on the ring and somehow bound to the same oxygen. They have to be pointing in the same direction in order to be bound to that same oxygen. So that means that when my nucleophile attacks, it's going to have to approach it from the opposite side, and I would specifically be left with that trans stereoisomer, where my two functional groups are pointed away from one another. All right, we wouldn't get a mixture of all possible products. We would only get specific stereoisomers. What's up?
In that case, is this just because we're putting the epoxide on a ring already, that's why it's going out of the plane?
It could have been, I could have put them both up, or I could have put them both down, but the point being is, like, if one was a dash and one was a wedge, there's no way for them both to be bound to that oxygen. And when we draw a bond, if we were to draw a structure like this, with just straight line bonds here, those lines are saying all possible stereoisomers are represented by that structure. And it's not true, because the one where they're pointed on opposite sides, that can't possibly exist. right? So we can only use our straight lines when it's representing all of the possible stereoisomers. If there's only a subset that are going to be formed, in this case either both wedges or both dashes, but not one and the other, we have to specify that in our structure. Okay? And it is, we will see it because it's a ring, right? So the ring is really what locked those on the same side of one another. Cool. All right. That's all we got for today.